Hello again. We are talking about improper integrals under the section of techniques of integration, and we're still talking about part 1 or type 1 of improper integrals, and that is when we have infinite limits of integration. And we see here we've got an integral here from 1 to infinity. We could have an integral from 2 to infinity, 7 to infinity, negative 500 to infinity, but we're going to see here for what values of p being a finite number, will 1 over x to the p converge to an actual limit or an actual area under the curve. This will become important in one of the tests for series convergence later on in the term. So I thought I could go over this in a separate video here, and I can refer back to it later. All right, so we're going to take this case by case. So for what values of p being any real number, so I'm going to split the real number line between negative infinity and 1 to infinity. So I'm first going to start off with p equal to 1. So for p equal to 1, does this integral converge? And I see what is from 1 to infinity of 1 over x to the 1 dx is going to give me just the integral from 1 to infinity of 1 over x dx, because I just replaced p equal to 1, and x to the 1 is x. We know that the function whose derivative is 1 over x is ln of x, and we'll go from 1 to infinity. Using our rules for taking improper integrals with infinite limits of integration, we will of course take infinity equal t, and we were going to say that this is the limit as t goes to infinity of f of t minus f of 1, or f of a from down below. And so I'm just going to take that limit, and f of t is going to be the ln of t minus the ln of 1. We do know that the ln of 1 is equal to 0. And if we plug in t equal to infinity, this is going to ln of infinity, which is going to infinity. So we know that for p equal to 1, the integral of 1 over x to the p from 1 to infinity of 1 over x to the p dx is going to be divergent. All right. So now we're going to take other cases, and we're going to say for p bigger than 1. So we're just going to say, okay, for p bigger than or equal to 1, we will have the integral of 1 over x to the p dx from 1 to infinity. We do not want to take the natural log, so we want to use our exponent rules, and we'll say that this is x to the minus p from 1 to infinity of dx. And using our power rule, since we have x to a number, this will be x to the minus p plus 1 over minus p plus 1. And we can see that that is going to be x to the 1 minus p over 1 minus p, and we're going to go from 1 to infinity. Good. And so for p bigger than or equal to 1, we know that 1 minus p is going to be negative. Right? And so if we have that this is negative over here, we can then say that this is going to be 1 over 1 minus p to x to the 1 minus p, or negative 1 minus p. From 1 to infinity, and we can see that that's going to be 1 over 1 minus p times x to the p minus 1, and p is going to be bigger than 1, so that's still going to be a positive number from 1 to infinity. Using our limits of improper integral, that's going to be the limit as t goes to infinity, this being t, of 1 over 1 minus p times t to the p minus 1 minus 1 over 1 minus p to the 1 to the p minus 1. And because p is bigger than 1, t stays in the denominator. So we do know that this is going to 1 over 1 minus p times infinity. Take away 1 over 1 minus p. And we can see that this is going to converge to 1 over p minus 1. So we can say that this is convergent. Okay, so we do know that for p bigger than 1, the integral does converge. Now, for p less than 1, nope, I'll take it that way. We still have taken our integral here. We can take our integral. We'll have that we've got x to the 1 minus p over 1 minus p from 1 to infinity. 1 minus p for p less than 1 is going to be a positive number. So with a positive exponent, we remain in the numerator, and so we're going to say that the limit as t goes to infinity with this equal to t of f of t minus f of 1 is going to be the limit as t goes to infinity of t to the 1 minus p over 1 minus p. Take away 1 to the 1 minus p over 1 minus p. Right, because all we did was replace our t with our x, and we're doing our f of b minus f of a, but we note that 1 minus p is positive, t stays in the numerator, so this is going to infinity over 1 minus p, take away 1 to the 1 minus p over 1 minus p, and that is going to infinity minus a number, which is infinity. So we know that for p less than 1, we have a divergent integral. So in a nutshell, or to summarize, the integral from 1 to infinity of 1 over x to the p dx is going to be convergent if p is strictly bigger than 1. So if that exponent in the denominator is strictly bigger than 1, it will be convergent for that improper integral, and it will be divergent if p is less than or equal to 1. All right, so just taking a look at these examples, I'm just going to use my exponent rules, and I'm going to simplify this expression here. 1 to infinity, that's going to equal 1 over square root pi times square root x dx. I can take out the constant, and that's going to, and I can convert my square root x to x to the 1/2, and I can see here that p is equal to 1/2, and I have that p equal to 1/2 is less than 1. So conclusion, my integral from 1 to infinity of pi square root x dx diverges. Good. And here I have, and it doesn't matter, we don't need to have from 1 to infinity. We can have from 4 to infinity, because if 1 to infinity converges, then 4 to infinity is going to converge. So again, I'm just going to use my exponent rules. This is x to the first power, and that's x to the 1/2, and that's going to be x to the 3/2. So if I have the integral from 4 to infinity of x to the 3/2, I do see here that p is equal to 3/2, which is bigger than 1. So we do know that we have a convergent improper integral. So I'm just going to go ahead and calculate that integral, and we have from 4 to infinity of x to the minus 3/2 dx, and that's going to give me x to the minus 3/2 plus 1 is going to be x to the minus 1/2 divided by minus 1/2. That's going to give me minus 2 over the square root of x. And we're going to go from 4 to infinity. And so that's going to give us the limit as t goes to infinity of f of t minus f of 4, and that's going to give us the limit as t goes to infinity of minus 2 over square root t minus minus, which turns into a plus, 2 over the square root of 4, and we are going to minus 2 over infinity plus 2 over 2, because the limit of a constant is a constant, and when we plug in infinity in the denominator, we're going to 0, and so we're going to 0 plus 1, which is 1. And so we do have that this integral converges to 1. Okay, so that does it for the very important property of the 1 over x to the p, and it will have huge ramifications with series tests in chapter 11. I will see you all at the next video.